Bueno, muchas gracias por la introducción y la invitación. So I will, in the interest of the audience, I will switch to English. This talk is going to be focusing on a method that is known as Approximate Bayesian computation, but it's using like a paradigm for doing inference that is known as analysis by synthesis. I will give more details about that. And how do we kind of make that inference in real time so that we can have autonomous systems or decision-making systems be able to do reasoning about sensor data, do predictions with uncertainty metrics on real time. Well, short disclaimer. This is also part of the project and the collaborations we are doing with various universities all over the world in the Intel Science and Technology Center that Nilesh already introduced. And this is related with the applications and algorithms part of the probabilistic computing stack. Let me give some ideas, some motivation. I will start with the applications we are showcasing the methods on, but we are using these kind of methods to do inference on a variety of problems. So you can use this, if you can frame it as an analysis by synthesis problem, you can use this kind of ideas for these kind of problems. In this case, I'm going to talk about predicting human intentions on like road scenarios, and predicting human manipulation intentions when dealing with objects on a table. Of course, this has applications to path planning in robotics in both scenarios. Like if you have robots that are able to infer, also having a measure of uncertainty of what people is going to be doing around, they can address, okay, with a certain degree of confidence what their actions can be, and they can avoid, like, for example, being stuck, like not knowing what people is going to do and freezing just because they don't know what's going to happen, or they cannot act with a degree of certainty that will ensure safety. These are the two applications I was talking about. It's predicting human intent. In this case, it's just a proxy of a manipulation task where we have a subject that grasps a ball and drops it on the table, and the system is going to give you a predictive distribution of what the user is going to do. And on the other case, we have a data set from an intersection in Germany that we use to test our algorithms on what are the plausible trajectories of the pedestrians, also with an evaluation on the uncertainty on how certain the methods are about it. We do this, as I said before, with analysis by synthesis, and we will, during this talk, see a lot of these kind of probability density functions represented as this color, where white or hot is like highest likelihood, and then dark is lowest likelihood. So you have it here and here. In these diagrams I will be showing, we will be using observations from sensors. In this case, the observations are trajectories. So this is this trajectory here is showing the observed trajectory, and here same thing. And then, well, actually they are flipped. This green one is the observation, and the other one is the prediction. But never mind. So we'll see a bunch of trajectories, and we will use the trajectories that are being observed to make predictions of what is the intention that we model with these density functions. So let's talk a little bit quickly about what inference with analysis by synthesis is. It's based on generative models. So we have a generative model that takes our, in this case is latent, but is designed by the designer that is creating the algorithms. I use this variable z here, and you have to take an initial guess of what's the latent state. And we also have observations that come from the sensors. So what do we do with those two things? We want to know what the value of z is in terms of, in this case, z is going to be what is the exiting point of the human through the intersection, or what is the final location of the human placing the ball on top of the table. And the observations are here information that comes from our sensors, and in this case is the trajectory that the cameras are observing. We get these variables into a generative model. I will give more details on the next slide. And this generative model provides us with some expected observations. And that's why it's called analysis by synthesis. You synthesize how your observations should look like if your hypothesis about the parameters is correct. You plug that into a likelihood model that is also designed. In this case, we'll be using just the difference between the trajectories that the generative model creates and the ones that we are observing. And through that, you can do some iteration using sampling methods to generate, every time you do a loop, one or multiple samples that you will be using to end up having your posterior estimate that would look like something like this. And this is what is the output is the system, and what we believe is a good input for decision-making systems that will be aware of, well, this person is moving that way, it's unlikely it's going to go to this area, but I don't know exactly where in this area that hand is going. That's more or less the idea we are after here. Problems. Well, in this case, for the trajectory, the generator or the generative model we are using is based on a physics engine that has a kinematic model and is running a dynamics simulation. So generating one trajectory to evaluate one hypothesis takes us 100 milliseconds. Well, we want to do this real time, and sampling algorithms require a lot of samples. So this thing is not going to cut it. We need something here. And another problem is that the traffic simulator we are using as a generative model for our traffic scenario, well, it's a standalone proprietary, so it's not easy to integrate into an inner loop of an inference engine. So that's another problem we have to solve. And the idea is, well, we just use one of these magical devices here. We plug in a neural network there, and I will explain how that is done. But we just replace this by a neural network that will be our generative model. But there are other problems. Sampling algorithms have some kind of limitations regarding multimodal distributions when you want to approximate, and there's a little bit of ambiguity on your underlying posterior likelihood. You might have multiple modes that will represent those different possible values. It will end up taking. And sampling methods, there are some that deal well with multimodality, but not. It's a well-known problem. And also the fact that most of them are iterative, that limits parallelism. And also, the sample efficiency is always another thing that we have to take into account. And these problems, we address them by one of the innovations we have here is the tripyramidal sampling. It's a sampling algorithm that we are using here. It's based on a quasi-Monte Carlo approach in the fact that it adds some structure to the sampling, so it will drive the sampling procedure a little bit better. Well, I have again here the analysis by synthesis loop. What do we do here? Well, we have the generative model, which I set the problems. How do we solve these problems? As I said, just throw a neural network on top of it. But then some other questions come, right? So how do we do this? It's easier said than done. You know, you have to trick and design the neural network, tweak a lot of parameters. Well, we generate a synthetic data set with the simulator. We are not limited in time for this, so we can offline generate a data set of plausible trajectories from this simulator, and then we can train the neural network to generate the data set, because that data set gives us the pairs, right, of inputs and outputs, so we can train a neural network. In this case, a fully connected network will work. and we just replace the simulator with this neural network. This is also, well, giving a little bit more detail. So we sample the parameter space, generate a lot of observations with the sampled latent parameters, and we built a data set. That data set is used to fit these theta parameters of our neural emulator by having a loss function that basically tries to match the trajectories of what the emulator produces. Well, how do we generate data without having a data set of humans? Well, in this case, we built this physics engine. Well, in this physics engine, we use PyBullet here, and we just have this. We built a robotics controller. So this robotics controller is tuned in such a way that it will generate trajectories that are robotic, because these are trajectories generated with a PID and the technology that the robotics community has. So trajectories might not look very human, but at least they satisfy several constraints that humans have: kinematics, dynamics, and avoid collisions. So at least we get a data set that will have this taken into account. And as you see, you need all of these parameters to create the simulator that we use to build the data set, train the neural emulator, and with that, what we can do is increase the speed of our sampling loop by, I think it's like from 10 to 100x. So it really puts us in the ballpark of the real-time inference. Here is a demo where I'm showing here like the real-time image. This video, the speed up is 0, right? So this is 1x video. There's a segmentation mask and the depth image that is used to detect the position of the ball. This is using a RealSense camera. And here you have the representation of what the algorithm is seeing and where the arm is. And it will look at the position, look at the trajectory as it evolves in time, and do the inference. And you will see the density of the number of points that we are able to achieve here. So you see when they start moving, you see how the likelihood or the posterior probabilities are continuously computed real time, okay? Here, that function that you see over there, it looks continuous, but it's not. It's just the density of the points. I cannot zoom in because I don't have the visualization here, but if you zoom in, you see the points. I think they are, well, maybe like 1 or 2 millimeters apart. So I could have this very nice, like continuously looking posterior. And this has another trick that I have to disclose here, is that because we know where are the possible locations that we want to sample, we can generate all of those trajectories offline. And here what I am showing is just these distance computations of the entire generated trajectories, a priori generated trajectories to what the hypothesis is. And what you can see here is that, well, in red is the current position, and then you see that the posterior, and also that blue dot that moves around that's the maximum a posteriori. Okay, so that's cool. We managed to get this real time working, but there's this catch, right? I just mentioned we are pre-computing a lot of things, so this is not. Oh, okay. I'll switch to this in a second. This is not all the accelerations we need to make this real time. There is a corollary I want to mention of using this method, and it is that we can also get that we can also classify how good the model is matching our observations, so we know how well how much we can trust the observations, or we can also use it to classify what observations we are seeing are not in our training set, which might be outliers. And that is very interesting to the pedestrian intent at traffic intersections. Here is the same I mentioned, but before for the human intent prediction, but for the traffic. So we have a neural surrogate that will be generating candidate trajectories. And with those candidate trajectories, we can do inference. And what we can do is that, okay, we have here overlapping the generated trajectories with the observations. They overlap quite nicely. So what you get from your prediction is that this epsilon, which is a slack term we use to account for the simulation to reality gap, is low. So that is telling us that this trajectory is something we are expecting to happen. But on the other hand, there are some times in this data set, for example, this is using real data. In this data set, there are some times that the trajectories that our model is generating, they do not match the observations because people is doing something weird, and that increases a lot this slack term. So the slack term needs to be cranked up so that it can cover that problem and match the observations. And interestingly, in these cases, there's a guy that's crossing diagonally. Again, this is an intersection in Germany. These guys follow the rules. And this guy is crossing without having the right of way. So you see how people that is following rules shows low slack on the predictions, and people that is not, it is crossing too fast. By the way, this work on the traffic was done in collaboration with David Gomez, that is just sitting here. So if you have a question about this, ask him. He's the guy. All right. So yeah, this is what I said about this sim to real gap that is modeled in this way. And now I'm gonna go through the update rule part of things, because yes, we can replace our generative model with a neural network, and that will speed up the inner loop of inference. But there is another thing that sampling methods use, and that's the update rule. So when you do, you sample from your prior, and that prior will give you an initial hypothesis. But once you evaluate that hypothesis, if you are using any kind of sampling method, like, I don't know, Monte Carlo Markov chain-based or nested sampling, or you are doing importance sampling, or kind of like population Monte Carlo, all the different sampling methods that exist, they usually require you to specify or to use an update rule that will tell you what is the next hypothesis you are going to take depending on the past that you had, right? So this thing, we also looked into it and implemented something that addresses these kind of challenges. That this iterative nature limits a little bit parallelism, so that will hinder the number of samples we can get per second. And remember, we want to do this to make this real time. And they have problems with multimodal distributions, and also they need a lot of samples to get to a good solution. And what we do here is we replace this update rule by this method that is we called three-pyramidal sampling. That is based on three pyramids that are a generalization of binary partition trees on 1D, in 2D is quad trees, in 3D is oct trees, in 4D is hexadeca trees, and then you can keep going, right? I'm not claiming that this works in n dimensions, because this still is cursed by dimensionality. So I wouldn't say in our experiments we have not gone beyond 6, 7 dimensions, because the things we want to infer are in general in those ballpark. Let's say you want to do object. One of the other applications we were is like object pose estimation. You want to estimate the pose of an object, then you have 6 degrees of freedom, so you move on those areas. And okay, let me go ahead and explain this. So this is how you usually see probability distributions. Here, this is a Gaussian mixture model with 4 modes. Actually, it has 5, but these 2 are collapsed here. And that's the representation by samples. So this is the sampled representation. And this is another example, a sampled representation of a banana distribution here. What do we use sample for? Well, we use samples because in general, when we want to do inference about this a posteriori or these posteriors, these are unknown. So we want to approximate them. You approximate them doing Monte Carlo samples, and you use the samples to compute values like expectations, entropy, or whatever you want to get from intervals you want to get from one of your PDFs. So, and sampling algorithms, well, you can do like you can scan for viruses. That's also you can do. Let's wait for an hour. And you can also like grid sample the space. Yeah, if your space is small and you don't need much particles, yeah, just throw a grid at it and just sample every point and compute the probability at each point. That's usually not a go way because it requires a lot of samples, and you will sample a lot in points where there's no, they are not important because there's no mass for the likelihood. So you want to do something more clever, like, for example, using the well-known Metropolis Hastings MCMC method, where you generate samples like this way. And I'm going to animate that. So that's how MCMC looks like. And you see it's generating samples from the underlying distribution. And what you keep from here after there's a burning period, so you discard some samples at the beginning. But this is told to, well, this is converging to the final the probability. And this is how it looks like. That's the same number of samples here, same number of samples here. And now this is how the three-pyramidal sampling works. This is actually not the last version of it, but it will serve as illustrative purposes. So in this case, we have a 2D space. This 2D space is producing a quad tree in these binary spatial part trees, in this binary tree in like multiple dimensions. And you see how this thing samples. And it is generating, again, the same number of samples than we saw before. But you see, because this quasi-Monte Carlo approach is prioritizing to take more samples where there's more probability mass. So you will get, just looking at it, well, you'd say that this is distributed as is, like this one. If you fit here, let's say you do kernel density estimation here and on the other probabilities, that's one idea how you can use to compare the methods. And well, first I'll show this work in real time. So you see that at every frame the tree is generated, and the number of samples you need to convert to a mode is reasonably low, that you can very efficiently compute it. Besides, the fact that you have in the tree multiple leaves that you want to sample from at the same time enables you some parallelism. We have not implemented this in a parallel way yet, but that's something I think we should do to properly exploit this idea. So in terms of result, this is, as I said, we do this kernel density estimation over the samples, and we get here that the three-pyramidal sampling, it ends up converging at the more or less the same location, but it converges faster, probably because we are still investigating this, but probably because this quasi-Monte Carlo structure that you are imposing onto the sampling scheme is driving the samples to be generated on these higher mass locations, and that reduces the KL divergence faster. This is with the first distribution I showed, and this is with the banana one, I believe. I forgot to add that, but yeah, I think that's it. Oh, no, those are different metrics. So the one is KL, the other is Bhattacharya distance, and the other is the expected mean square error. Oh, well, this is another plot that shows how the method performs. And you see in this part here, on the right, there is a cluster of methods. Those methods are using the different sampling techniques. Let me read that for you. So one is particle filter, binary space, well, the three pyramids, ABC reject, ABC sequential Monte Carlo Markov chain. So those are the four methods. And this one in green is our method. So it goes low in error and low in time for this cluster that is not using the neural emulator. So we are not emulating the generative model here. And here, by emulating the generative model, we get all the execution time lower, which I cut that but this is log scale in the x-axis. So you get that, and that's the 33 millisecond line. And that line, you could go with maybe, I'd say, 50 milliseconds to claim this will work on cameras and real scenes. But given that the sampling rate of the sensor we are using is 33 milliseconds, I put the line there. And we see that just by using the neural emulators, there are several methods that put us on the right spot. But that's also good that by using this, I'd say, more principle, well, not more principle, like this more directed sampling idea, you get better in execution time. And yeah, I guess that's all. So summarizing, we introduced these neural surrogates and the pyramidal sampling to increase the speed of ABC, which is well known by statisticians not to be real time. So that's a method that in general is not used for this. And yeah, I have just shown how to apply them. We are still investigating in these areas. And yeah, that's all I had. So yeah, thank you. Yeah. My, what? The personal?
No, just something like this.
Okay.
Do you have the examples where something like goes in one direction and then changes their mind?
Yeah. Yeah.
Do you
Let's see.
There's difference between does this method get kind of stuck going
I would say, well, what I have seen from experience, actually, that video is what happens next, like I think Javier. But I do like this, right? So I grab the ball and then I do it. And what happens is that, well, there are two things. This has never seen a person. So what I observed, we have a demo as well of this. And what happens is that the predictive distribution is too wide. It's too wide for what I would use, right? So that's why I say we are investigating still. But this also telling me that the generative model is not that good. It comes from just a motif controller, and we need to find a trajectory that is more proper. When I try to do this and pull it, here down below there's like this slack term I was mentioning. It tends to increase, but that's not a claim I could support because I have not evaluated what happens if you do it. I just tried the method. I mean, that's not explode, that's not diverge. So it's still, I would not say it widens that's what I would like to see. It's that it widens the distribution. But I think is that what eventually will happen. It just moves the prediction left and right, trying to follow you, but it gets behind. I think it loses a bit the predictive power because it has not been trained with those kind of samples. We are using the neural emulator.
There's not it's not like the tree pyramid just falls apart because of the other.
No, what I would say is that the tree pyramid will start increasing the computational demands because the sigma of, well, the entropy of the predicted distribution will grow, and it will require to spread more the samples and need more samples to make a good approximation. Oh, well, that's a PyBullet. That's an implementation of in Python of Bullet. It's a game engine.
Thank you.